This video is sponsored by Brilliant. The biggest source of methane here on Earth is flatulent cows. That's right, cow burps and cow farts. Now, the methane technically doesn't come from the cows themselves, but from the microbes that live in their gut that help them digest all of the plants that they eat. Once the digestion is done, the cows pass the methane gas and it enters our atmosphere and becomes a greenhouse gas and contributes to global warming. But what has that got to do with Mars? Well, because of its connection to life here on Earth, it's been considered for a long time a potential biomarker, a signature that life, at least microbial life, might be present on another planet. Science is never that simple though, because methane can also be produced in geological processes, by rocks. So when the first detection of methane in the Martian atmosphere was made back in 2014, people were obviously excited, but also cautious as well. We had to repeat the experiment. We'd need more measurements from other satellites and rovers and landers to confirm whether methane had actually been detected. Little did they know then, though, that all those extra measurements would just lead to even more confusion and a scenario that we're only just beginning to explain. Kind of like a science whodunit. This is the story of the Martian methane mystery. Now, methane on Mars is nowhere near the concentrations that we see here on Earth. In 2019, the methane concentration in the Earth's atmosphere was measured at 1,866 parts per billion per volume. On Mars, it's more like 1 parts per billion per volume. To put that into context, it's like a little pinch of salt in an Olympic-sized swimming pool. And that's not even a real exact measurement. It's actually what we call an upper limit. Essentially, we know the methane has to be less than that, otherwise we would have detected it in all the experiments that have been run over the years, either with telescopes here on the ground or satellites in orbit around Mars, and even Curiosity rover, when it landed on Mars in 2012, it put a limit on the amount of methane in the Martian atmosphere of 0.5 parts per billion per volume. That's barely anything, right? It's nothing to write home about. So off Curiosity went doing other things. But then in 2014, Curiosity detected spikes in the methane concentration over the span of about 2 months. They averaged out at about 7.2 parts per billion per volume. And it's also seen the normal concentration of methane changing with the seasons as well. That means something on Mars is producing methane seasonally, but also with these random spikes as well, and we just don't know what it is.
It just got interesting!
Now, since 2018, a satellite that's in orbit around Mars, ESA's ExoMars Trace Gas Orbiter, has been continuously searching for signs of atmospheric methane. Now, the methane detector on ExoMars is supposed to be the gold standard for detecting methane. It's used in industry on Earth loads. It's also used on the ISS as well to give advance warning to astronauts if there is like a methane leak or something. But on Mars, this gold standard detector didn't detect any methane in the Martian atmosphere. And so Curiosity's detections of seasonal variation and random spikes were then massively brought into question if the thing that's like the gold standard didn't detect anything. Now, ExoMars is only sensitive to methane above about 3 kilometers in altitude in the Martian atmosphere. And also, its limit on the amount of methane it can detect is only 5 parts per billion per volume. You might be thinking, well, what Curiosity detected was lower than that. But the problem is, if this methane is perhaps being released, let's say by the Martian rocks or something like that at the surface, continuously, and Curiosity is able to detect that amount that is being pumped out, that should slowly build up in the atmosphere, get well mixed, and should get above concentrations that ExoMars should then be able to detect. But that's not happening. At the rate that Curiosity is detecting at the ground, that if you assume that that's what it's pumping out, it should have built up to a concentration that ExoMars can detect in about 28 years. It's highly unlikely that these methane emissions from the ground have only just started in the past 20 years or so, when Curiosity just happens to have landed on Mars, when Mars has been around for 4.5 billion years. So once again, that leaves us with this discrepancy between what Curiosity measures and what ExoMars measures. It's a classic science mystery that needs solving. And so the Curiosity team especially put their heads together and were like, what could be the possible explanations for what we've seen? And the first thing they started with was, is the rover itself giving out this methane? Perhaps by rolling over rocks and crushing them and releasing any trapped gas. But the spikes in methane it detected didn't correlate with any movement of the rover. The rover was always still when it took those measurements, so that was quickly dismissed. Then the next idea was, well, could there be some methane leaking from other instruments and detectors within Curiosity rover itself? But, every system was double and triple checked, and they're pretty sure there's no methane leaking from the rover. The next idea was whether these methane spikes perhaps correlated with a direction that the rover was facing in, perhaps towards a certain rock formation or something that might just be a very high concentration of methane. But again, no, there was no correlation there. And similarly, there was no correlation with wind direction either. Perhaps the wind bringing something over from a very high concentration of methane somewhere. All of those ideas were thrown out. But then one of the Curiosity team scientists, Dr. John Moores, had an idea. And he said in an interview with NASA that he took a very Canadian way of looking at this and said, what if both Curiosity and ExoMars are both right? And I just love this very Canadian way of looking at things. Because they realized there was a correlation with the time of day that the measurements were taken. Up until 2019, all the methane concentration measurements that Curiosity have made had happened at night, when there wasn't much else going on with the rover. So what the team did was then measure the concentration of methane during the day and noticed that it was much lower. It dropped to 0.05 parts per billion per volume, down from the 0.5 parts per billion per volume that averaged out over the nighttime. So I guess that's kind of like a 10% of a pinch of salt in an Olympic swimming pool. Scientists should never write recipes. I'm just going to put that out there. And guess what? The ExoMars satellite had only ever taken its methane concentration values during the day because it physically needs sunlight in order to be able to make the measurements. So all of those measurements, the day and the night concentrations, have been explained in a paper published recently by Webster and collaborators, which I'll link in the description below if you want to check it out. And the way they've explained this day-night difference is due to the weather, essentially. So at night, it's much cooler. The atmosphere is much calmer, and methane seeping from the rocks due to whatever process is building up at the surface, essentially. But when the sun rises, it starts to heat up the air. And then that sets up a classic weather pattern of hot air rising, taking the methane with it, and then cold air falling. And that mixes it all up in the atmosphere, lowering the concentrations to below what ExoMars can detect during the day. So that study at least gives us one possible explanation for the discrepancy between the Curiosity and the ExoMars measurements. But it still leaves a whole boatload of other unanswered questions. The first of which just being, what is producing this methane on Mars? Especially these weird spikes and this seasonal variability, which is, to be honest, just weird. Although given the fact that the weather explained the last problem, it's likely that something to do with the sun and solar radiation could explain this seasonal variability as well. Perhaps in the summer, there's more incidence of solar radiation that melts some ice, trapping methane gas that's perhaps trapped underground. So we don't know how it's gotten underground, whether it is just coming from rocks, or maybe there's some microbial life living underground there, perhaps releasing methane. We just don't know. The second question that still remains is, why isn't this methane, which is coming from rocks or microbial life, we don't know, why isn't this methane building up in the atmosphere over time? Curiosity landed in Gale Crater, and that's where it's detected these higher concentrations of methane at night, and including these spikes as well. Now, we don't think there's anything special about Gale Crater. If Gale Crater is emitting methane, then probably the rest of Mars is too. So it should have built up to concentrations that ExoMars can detect, but it hasn't. Now, we know that methane is stable in the Martian atmosphere for at least 300 years before it does get broken down by the impact of solar radiation. But 300 years is still enough time for it to build up to concentrations that ExoMars can detect. So there must be something else, some other process going on that is somehow destroying the methane. And whether that is perhaps, just reabsorption by rocks of the methane. People have proposed the idea that static electricity generated by the dust storms and sandstorms that we see engulf Mars occasionally, that could actually be creating static electricity that could destroy the methane. Or perhaps maybe it's reacting with oxygen in the Martian atmosphere as well. Oxygen is very reactive and perhaps that's getting rid of the methane. There's lots of ideas, but we still don't know which one is actually happening. Either way, whatever is happening on Mars, this study that's come out this month has at least given us one piece of this very confusing puzzle. But rest assured, there is still a whole heap, a truckload of unsolved Martian methane mysteries. Before we get to the bloopers, a huge thank you to this week's video sponsor, Brilliant. Brilliant is a website and app with interactive learning courses on a huge range of science and maths topics. Now, you've probably heard me talk about Brilliant before, but recently they've upped the interactivity on their courses to a whole new level. And this is what impresses me most about Brilliant, is the fact that you can really engage with the topic and learn by doing, which has always been my favorite way to learn something new. When people tell me they want to become scientists in the future too, one thing I always tell them to learn is how to code. But that might not be intuitive at first. It definitely wasn't for me. So check out Brilliant's Algorithm Fundamentals course. It takes you through pseudocode to the commands computers use and gets you thinking about processes that a computer follows in a step-by-step way, sort of getting you thinking like a computer so that it is a little bit more intuitive for you when you come to coding yourself. So if that sounds like something that you'd be up for, then head to brilliant.org/Dr. Becky and sign up completely for free. The link is in the video description down below, and the first 200 people that go to that link are going to get 20% off an annual premium subscription. So thank you so much to Brilliant for providing you guys the opportunity to learn and for continuing to support this channel. But now, roll those bloopers. Was 1,866 parts per billion. Parts per billion? Parts per billion per volume. I'm going to trip over that so much in this. I can tell. On Mars, however, the methane concentration is more like 1 parts per billion. Per billion! Oh my god, I just said it again. Parts per billion per volume. It put a limit on the amount of methane in the atmosphere of 0.5 parts per billion per volume. And it can only measure down to about 5 parts per billion per volume. Per billion. Why? Why?